Well, welcome everybody. Yes, my name's Steve Rolston. I'm the founder of Landark Homes, and today I'm here with Kevin Rankin, our general manager, and with Will Beardmore, our expert from Bluewater Energy. So I'm going to hand things over to Will in just a moment, but we want to welcome everyone and thank you for making time to be here. The video will be open just to ourselves for the time being. And the Q&A, we're going to have Will answer everything at the end of this. Once he's done his 40 slides and maybe 40 minutes of presentation or thereabouts, and then we'll have 20 minutes of Q&A afterwards. But Kevin, do you just want to say anything before we get started here?
No, it's good to be with you, Stephen, and great to be with Will. Just to let everybody know, we've had a chance to get to know Will over the last couple of years as part of the Net Zero Council. So Will has been a long time leader in the solar energy space for high performance home builders in Canada. So really worked across the country with leading high performance home builders. And what I think, and we'll let you know, kind of Will's going to run with the show here, but I just want you to tell you, having sat through a number of sessions with the builders like Landark that are really trying to change the face of the building industry to building better homes, building better communities, and offering up these types of options to the homeowners. We're absolutely convinced that Will is going to be a huge part of helping all us and our homeowners work with the local utility and come up with some wonderful solutions. We believe the time is now, and I'm going to let for solar, and Will, who's been working hard at this over a decade or more, can jump in. So thank you, Will, for being with us. We're very grateful, and we think your expertise has already moved us forward in good ways.
Well, thank you, Kevin, and thank you, Stephen, and it's a pleasure to be here. Those are big shoes to fill, so I will endeavor to do so, Kevin. Thank you. All right, so we, in the interest of presenting a fair amount of information here in a reasonable amount of time, we don't have the luxury of a long format and getting really, really detailed in some of the things that we're going to be talking about. This is meant to be a high level presentation, and we do want to leave time for questions at the end. So therefore, I will cruise through things at a pretty steady pace, touching on the areas that I feel are critical, and then there will be probably many things left unsaid and questions unanswered, but hopefully we will leave this presentation a lot smarter than we were when we started it. So what I'm going to talk about here is solar photovoltaics, and short for photovoltaics is PV. So when you hear the word or the term PV, stands for photovoltaic, which means voltage from light. And we've had the honor and the pleasure of providing some of our services to Landark, and we actually are currently in the process of installing a PV system with some energy storage on their model home in Watercolour Westport. What you see on this picture here, this is an office building that we put solar on the roof of, which didn't quite get us enough generation to offset the consumption in the building, so we added a solar awning around the outside. Okay. There we go. What we are going to talk about, first I'll cover some solar basics, because I think it's always beneficial if we have some operational definitions and some common language from which to speak and understand. Then we're going to talk about whether solar panels for the home are still worth it, and is solar worth the cost, because it is not an inexpensive endeavor. But so we'll talk about the financial business case there, even for residential homeowners. We'll talk about monitoring system performance, and then we'll leave time for some questions. Okay, so solar PV basics. This picture here actually is of the first net zero community that we were a part of, and it was one of the first official net zero communities in Canada, and it happened in Guelph. It was under a National Resources Canada pilot program, and we provided the design and the build for the solar arrays for this community, and there were 5 homes involved. And so you can see that picture here. This was back in 2012. Solar has evolved, quite a bit since then. It's a short period of time, but we've seen some pretty big leaps in terms of efficiencies of solar modules and some of the technologies. Most particularly, the thing that has changed the most significantly has been electric code, and it keeps iterating and evolving to ensure that the way things are being done are safe for buildings and the occupants therein. So solar PV modules. So what we term to be a solar PV module is each individual, as you would probably have heard them termed, solar panel. So each PV module within an array generates DC power, that's direct current. And you can think of a solar array as a DC generator and the fuel for that generator as the light from the sun. The average efficiency of a PV module is between 20 to 22 watts per square foot, and a typical PV module is approximately 18 square feet. And then the average capacity of current modules is about 400 to 410 watts on this footprint. So, that means that we're now what we were, the amount of square footage we needed to do 10 kilowatts 10 years ago has essentially decreased by almost 60%. And so where we needed 1,000 to 1,100 square foot of roof space to do 10 kilowatts of PV in 2010, 2011, we now only need 400 to 500 square feet of roof space. So it allows us to achieve a lot more, and it's allowed us to actually achieve the targets of net zero home construction. And the average PV module, this depends greatly on pitch of roof and orientation of home, but will generate anywhere from 1 to 1.5 gigajoules of generation per year. We'll talk about gigajoules and other sort of energy constants in a moment here. All right, the solar PV inverter. So the inverter is essentially the brain of the system, and what this does is this converts the direct current power, which is generated from the PV system, the solar array on the roof, and converts it to AC power, which is alternating current, which is the power that we get from the utility grid. So when you plug something into a wall in your home, when you turn on an appliance, the electricity that is providing the energy source for our use is alternating current, 60 hertz, 240 volt, or 120. And so the inverter here takes the power that's coming off of the PV system, converts it from DC to AC, synchronizes it with the grid, feeds it into the home, and it actually provides a pure, clean sine wave. So in terms of power quality, it is as good as it gets. Locally generated power used at the source or within very short distances of the source with modern power electronics, which solar inverters are, provide extremely clean energy, and even more so than what we experience from the grid typically. Mounting the PV system on the roof. We often get a lot of questions as to how the system mounts to the roof and what the implications are in terms of integrity of the shingles, weatherproofing, longevity, things like that. And so this picture here is meant to, sort of visually show you how we do that while I sort of talk through it. And so what happens is that we, you can see here these black squares. They are what we call flashings, and they're made out of aluminum and they're powder coated. And what happens is we attach a lag bolt with a base plate through the roof into the top cord of the truss, and then we cover that with this aluminum flashing. So every attachment point is essentially a lag bolt, which is a long screw that goes through the roof into the wood member that is the framing of the roof on the underside. And then we seal it, and then we tuck it up under the course of shingles that are above it. So any water coming down the roof essentially hits this flashing and the penetration point is now underneath the course of underneath this this aluminum flashing, which is tucked into the shingles above. So water does not have the ability to get into or around or near the hole that we've put into the roof to attach to. And then the mounting structure attaches downslope of that. So this L bracket here is now bolted to the base plate, which is underneath this flashing, which is secured to the roof up slope here underneath, and then that supports the rail system. And then the modules are then mounted onto these rails, onto the rail system. And so that's how we ensure weatherproofing. They're mechanically tested, they're wind tunnel tested, and they're engineer approved, and they meet all Ontario building code standards. They're flashed and sealed, so we have no issues with water egress, and a properly installed solar array is not going to have any issues in terms of weatherproofing, just for some peace of mind there. So solar PV connection, I'm going to cover this in 2 slides. First of all, here's the hydrometer. Everybody's familiar with that. I showed the inverter previously, and I'm going to show you how all the components tie together. But essentially out of that inverter, we come out to this disconnect switch here, which is required by code and by utility standards, so that there's a means to shut the solar PV system down if it's ever required to do so. And really the only times that's going to be required is if there's work being done on the lines by the utility crew, and they want to make sure we're not feeding anything back onto the lines and energizing the distribution system while work is being done, so it can be done so safely. And this is just to show you that, you know, there will be some visible signs of a PV system on your home, and one of which is this switch that has to be installed within 1 meter's distance of the hydrometer. Okay, and so how do we connect the solar to the home? So I think most people are probably familiar with your electrical panel in the home. Probably not a lot of people have taken the cover off and had a look inside. So this is what it looks inside. These are the conductors, the wires that come from the utility, from the meter into the main panel. And then from there, all of the breakers essentially feed the loads in the home. So what we do is we'll bring the solar in, and we'll connect the solar right here into the top of the electrical panel, and we'll feed the solar generated power right onto the electrical panel, which will then have the effect of either supplying all the loads in the home or going out to the grid. And I'm going to talk about how that all works in this slide right here. Okay, so this is to visually sort of help you understand all the components. Now, it's in the style of a single line diagram, which might not be intuitively or necessarily familiar, so I'll explain it. So this is the rooftop solar array, and you can just sort of visualize we've got solar panels on the roof here. And as I said, they generate direct current electricity, and that electricity comes down and it comes through the inverter. The inverter converts DC to AC, alternating current, and then we go back outside to that disconnect switch that I showed you in a previous slide. And then we come out of that disconnect switch, and then we feed into the main electrical panel, which is right here. And so this is how the electricity is delivered from point of generation, which are the solar modules, to point of use, which is the electrical panel in your home. Now, what happens is electricity is consumed in the home first and foremost, and then any excess goes out through the meter and then out to the utility. The meter measures electricity traveling both directions, into the home and out of. And then I'll explain sort of the net metering policy here in a few slides, but essentially you are billed the net difference between what is sent out and what's actually consumed. Okay. Any questions so far, Stephen or Kevin, or any points?
Nope, keep her rolling there. Will,
right.
You're doing great. I love your presentation style.
Okay, thank you. All right, so let's talk about whether or not solar panels for the home are still worth it. And so the answer to this question in short is absolutely, and becoming increasingly more valuable to homeowners as we sort of move forward in time here, particularly when we talk about the decarbonization, electrification, energy transformation goals and targets that are being laid out at all levels of government, municipal, provincial, federal. And so one of, if not the best way of achieving our goals is through distributed energy resources like solar at the residential level, giving personal autonomy and power back to homeowners in energy use and management. Okay, so I'm going to talk you through the process that we went through with Landark's model home and that we are currently going through for every one of their homes that they're building in Watercolour Westport, just so that you have a clear understanding of how the process works and how we arrive at the size of system that we need and how it's laid out, and how we can assure that it's going to achieve what we aim and require it to achieve. So it starts with the home energy model. And so Landark has an energy management consultant and company that does an energy model for them that is based on the construction of the home and the mechanicals that are being selected for the home, insulation values, air changes, windows, things like that. And so with all of that information, National Resources Canada has built some tools for energy managers to use to be able to determine how much energy the home is going to consume over the course of the year. So for the model home, that came out to 48 gigajoules. 48 gigajoules converts for our purposes into 13,327 kilowatt hours per year of electricity. Okay, so that's how we arrive at our target for what our system needs to produce over the course of a year. So we take that 3,327 kilowatt hours, 48 gigajoules, and what we do is we sort of break it down into a monthly consumption pattern. And this is based on our own analysis of homes that we've been monitoring for quite some time. So it's by no means universal. It's by no means, official. It is our own observations that we've arrived at this distribution. And the reason we do this is because we want to compare monthly consumption versus monthly generation. So once again, 48 gigajoules, 13,327 kilowatt hours a year of energy consumption. And then we can now do what we need to do to determine the size of the PV system that's required for this home. So where that starts is we get the architectural plan set from Landark. We get the site plan, which shows us how the house is actually going to be situated, so which lot it's on and which direction it's going to face. And so we see the north arrow down here. We see the front of the home facing down this way to Shelter Cove Drive. And now we know essentially what the home is going to look like and what direction it's going to face. And then we also take the shop drawings for the roof truss plan, so that we know, so that we have the ability to create a 3D model. And so from these three documents here, we are then able to go to work. So we take the roof plan, and then we create a scaled model in our software, which we can then turn into 3 dimensions, and we can ensure that the front of the home is oriented according to how it's actually going to sit on the ground. And the colors on this image here represent efficiencies of the roof. So once we have the 3D model, this gives us the accurate pitch of the roof. It gives us the accurate orientation of the home. And then our software allows us to determine which of the roofs on the home would be the most efficient for installing solar. And so where you see the lighter colors, those are the more efficient orientations, and the darker colors are the less efficient orientations due to tilt and direction. And why this is important is because it focuses us in quickly on which roof planes we're going to start applying solar modules to, first and foremost, so that we can achieve the generation target that we're after. And the reason we want to start with the most efficient roofs first is the more efficient the roof is that we're installing upon, the fewer solar modules that are required in order to achieve the annual output that we're looking for. Okay, so the next step is we take that home, and again, now we've just oriented it so that north is up, and then we can get a clear indication that the front of the home is facing northeast, the rear of the home is facing southwest. The rear of the home, nice big open space for us to work with, most efficient roof. So this is where we started. Then we start applying solar modules onto that roof, and we run our generation model to determine how close we are or far away we are from our target. And so where we ended up here is the azimuth of this roof faces 225 degrees southwest with a pitch of 26.6 degrees, which is 612. And then what we ended up requiring is 27 PV modules in this scenario at 395 watts a piece. And then we end up with our design as such. And so this is now the PV system as modeled for us to move forward with and create our building permit drawings and our electrical drawings for the utility. And so it also gives the builder and potential home buyer or client the opportunity to see what their home is going to look like with solar modules on it, so that before you even take possession of the home, before you even see it, you're going to understand what the solar modules are going to look like. Point to note, we generally avoid putting PV modules on the front of the home simply because most people are still haven't yet adapted to the idea of, you know, that being a part of the facade of the home. Sorry, one moment. Sorry, had a little guest just show up there. Okay, I guess these are the things that happen. My apologies. Okay, so now how do we determine what this system is going to generate from having the model, from having it laid out, oriented, and tilted in the direction that it actually is going to be by the home? And so the way we do that is we use our model that creates simulation, and we input simulation factors. And so we take the irradiance of the site, and that is of the geographical location of where the home is going to be constructed. And we reference the nearest weather station, and we access 50 years of meteorological data for our model. And that gives us a minute by minute irradiance at the site for us to then work with, so that we can input our factors for this home that will then end up giving us the generation output for the year that we're looking for. And so we adjust for tilt factor if we're less than ideal, how the array is oriented by horizon, any shading factors, soiling from dust and debris and dirt in the air, particularly in a construction site, snow accumulation on the modules, incident angle, which is how the modules vertically and horizontally sort of differ from the ideal. And then we get an irradiance that we're going to experience on the solar array itself. And then from there, we take additional loss factors for environmental factors, which are like temperature, winds, things like that. Module rating. So are the modules outputting exactly what the manufacturers have specified? We factor in an annual degradation of module performance. We factor in losses for connections and module mismatches and DC wiring. And then we factor in additional losses for the DC to AC conversion. And what we end up with at the end is a very realistic number in terms of how much power the system is going to generate. And we've been doing this for almost 15 years. Actually, this is our 15th year, and we have thousands of systems installed that we compare actual versus forecast generation. And what we're seeing is that typically we're within 2 to 5% of that number. It will vary year over year, because we never have exact sort of same weather patterns year over year. So we will see that affect generation output typically in any given year. And then what we end up with is an annual production forecast from the model based on the system that we've designed here and the module that we've selected. And again, we ended up requiring 27 PV modules, which gave us a total DC generation capacity of 10.67 kilowatts and a max AC output of 10 kilowatts. That allows us to generate and offset 13,404 kilowatt hours a year. And so we are in fact net zero on this home. Now the green bars here are the monthly generation of electricity throughout the year. And the light sort of grayish green bars are the consumption that we converted our annual gigajoule from the energy model into. And so we can see that where we have more consumption in a month than generation, we're consuming a net amount of energy from the grid, and where we have more generation than we have consumption in any month, we're exporting a net amount of energy to the grid. And so the net exported versus net imported, or net overall use for this home on an annual basis, is actually 0. And so this sort of visually gives us that representation a little bit better. Orange is consumption, yellow is generation. And so the exported amount sort of accumulates as credits on the bill throughout the summer months, and then it gets applied to the bill throughout the winter months, leaving the homeowner with ideally no electricity charges over the course of the year. And that's what we typically see for a net zero home. Okay, so I'm going to stop, take a little pause there. Kevin, Stephen, do you have anything to add or any questions at this point?
Yeah, that was fabulous. Will, I just learn, you know, I learn a little bit more every time I hear you. I think there is some, I just wanted to make a comment. Maybe you can answer that. And we do have one audience question, which is probably great to answer at this point. The thing that I think is fascinating is to, you know, just hear the level of, you know, of detail that is part of the modeling exercise to make sure that, you know, we're that you can, you know, kind of hit the end goal of having a sort of a net $0 from an energy usage standpoint at the end of a 12-month period. So I think maybe you can just clarify that in some, you know, you model it, the exact location, the elevation, the, you know, the versus the horizon, and what's fascinating to me is that perhaps you could also comment on the fact that the modeling that the energy advisor does takes into account those same factors. So not only are you doing it in terms of generating, but if I'm not mistaken, the energy consultant who does the modeling of the energy usage goes into that, you know, has that same level of analysis, so that we've got a reasonable, you know, estimate. Obviously, different people use their homes differently, but maybe you can just comment on the fact that this is from the design and modeling standpoint all the way through to the implementation standpoint.
Absolutely, and I think it is important to actually highlight something you just said there, Kevin. The homes are net zero as designed and not necessarily net zero as operated. And there's a big distinction there, because the required amount of energy factored in by National Resources Canada's standards into the model is 19 gigajoules for occupant load. And that's actually a pretty significant amount of energy. But if we have a situation where, you know, there are 2 electric vehicles charging, there's a pool and a hot tub, then there's more energy going to be consumed on the operating side. But on the design side, you're absolutely right. The energy consultant will take into consideration the orientation of the home and the location. And so we have 6 climate zones, 7 climate zones, going down to 6 climate zones within Canada. So the actual geographic location in terms of latitude matters. And so depending on which climate zone you're in, there's different modeling data. And then, you know, the orientation of the home in that location is going to be significant in terms of what direction is receiving the greatest amount of sunlight, how many windows and how much glass is on that side of the home, what are the ratings for those windows in terms of UV and solar heat gain, heat loss. And then in addition to that, in terms of heating and cooling loads within the home, the energy consultant is going to determine, based on orientation of the home and the mechanical systems and the insulation and air changes that the home is modeled with, is going to take into consideration what the heating load and what the cooling load is going to be throughout the year. And so all of these things are factors that go into that model on the energy consumption side of the net zero equation.
Yeah, fantastic. Really helpful. So Stephen, there's a couple of great questions here. Will, how do you feel about just maybe answering a couple of these, and then we'll sort of dive into the end? Because I think there's one slide that you just showed, which maybe we should just touch on, and then we'll leave the other questions to the end. Will, you showed in your modeling, the question is, do your calculations take into account the degradation of the modules over time? So I think you kind of ran by that, and maybe we can just highlight that again.
Yes. So in fact, module manufacturers will specify that crystalline silicon, essentially, or that's what the cells within the solar modules are constructed of. Crystalline silicon will degrade over time, and manufacturers will specify what that level of degradation they expect from their product. And typically that's somewhere between 0.3 to 0.5% per year. And so we factor that directly into the model. And we factor in a 1% loss from degradation in our generation forecast. So again, we do model on the conservative side, which is, we're not sandbagging here, but we do want to make sure that we're not providing a solution that overstates what it's actually going to be able to deliver. So typically speaking, as I said, we're within 2 to 5% per year of forecasted versus actual, but we do put that directly into our loss factors. Yes.
Fantastic. This is great. We'll let you continue on to the next section. Start getting into some numbers. So that's great.
Okay, well, thank you. All right, so is solar worth the cost? Well, I mean, this is ultimately something that matters to most people for sure. And we find that the principal reason is financial benefit, with environmental benefits being slightly secondary, but to be honest, most people have to factor in the financial implications in a decision like this. So how does a homeowner financially benefit from solar? And that happens through what we call net metering. And net metering is a program in Ontario that is governed by an Ontario regulation, which is law, which directs local distribution companies, which are the utilities, to allow individual homeowners to have locally generated power on their home, feed their needs, as well as export excess to the grid up to a certain amount. And so the way this works is, again, we're generating power from the solar array. We're converting that power from DC to AC, and we're sending it into the home, and we're consuming the power in the home. When the sun is shining and we're generating more power than is being consumed in the home, excess is going out to the grid. It goes through the meter. The meter measures in kilowatt hours how much energy is going out. That energy that hits the grid is then available for use for other people on the distribution system, and typically it's going to be the immediate neighbor left and right, or somebody very close within the community, because we're not talking about substantially large amounts of exported energy. We're talking about a few kilowatts of energy at a time at most. And so there's no significant impact to the grid or the distribution system through doing things at the residential level like this. When there's not enough sun to drive the solar array sufficiently to meet the demand for electricity in the home, then any amount of electricity that is being generated is being fed into the home, and then only that amount more that is needed is brought in from the grid, and the meter measures the energy that's coming in that way. And so what happens is the monthly bill is reconciled to take into account how much is used, how much is exported, and the homeowner is billed the net difference between the two. And so that's how the net metering works. What I do want to talk about are electricity rates quickly, because it's important to understand how net metering impacts things. So we have what are called time of use rates in Ontario, as well as flat tiered rates. Current time of use rates are 7.4 cents a kilowatt hour, 10.2 for mid peak, and 15.1 for on peak. Now, the default when a homeowner starts to net meter is that the utility switches your utility rates to tiered flat rate. And the tier 1 rate is 8.7 cents and the tier 2 is 10.3 cents. The reason I bring attention to these is if we are not net zero, if we're net zero, this becomes a moot point. We don't have to actually even worry about it because we're offsetting 100% of electricity consumption in the home. If we're not fully net zero, and we are seeing actually a greater number of homeowners sort of start with a smaller system with the aim of producing enough energy to offset mechanical loads and some operational loads, but not necessarily 100% of their lifestyle loads. And so, if we're operating the home primarily in off-peak hours, and we're not offsetting 100% electricity with solar generated power, then time of use rates are the best rates to choose for the homeowner. If we're operating the home primarily in the mid-peak and off-peak hours, then the best rate structure for a homeowner is the flat tiered rate. Okay, and so this is a copy of a Hydro One bill. We're gonna put a Landark bill in here once we have the net zero home operational. But just for clarification purposes, there's a couple of parts to the bill. One is the price for electricity, which is the cost per kilowatt hour, and the other is the price for additional charges, which show up as something like delivery expense, which includes delivery, transmission, distribution charges. Now, these are also associated with the amount of electricity that is consumed within the home, so per kilowatt hour charges. Okay, so that's just sort of for some clarification. Now, here's what hydro rates have done historically since 2006 until November 2022. We have seen some down, some flat, some slightly up, some steep up, and then some more down flat. So hydro rates over time have increased 7% since 2006. And this is important when we talk about the financial model for homeowners who are considering solar installation. Now, what a kilowatt hour of exported energy, purchased or exported consists of is the electricity rate, those distribution and transmission charges, global adjustment charges, wholesale market charge. Where you see the check mark here is these charges are offset by a kilowatt hour of energy exported to the grid. These charges are not offset by an exported kilowatt hour of energy exported to the grid. So you're still going to have the fixed monthly charge, and we're still going to pay HST on the total amount of electricity consumed, whether or not that amount was offset through credits. HST still gets paid on the full amount, just so that we understand the full picture here. Okay. So a net meter bill looks something like this. It'll say, here's how much energy was consumed over the course of the month. It'll say, sorry, down here. So this is electricity rates, an amount of electricity consumed, which translate into expense, delivery and regulatory charges here, debt retirement charge, which we don't currently have, but I think we can anticipate in the near future, and then total electricity charges. And then over here, we see the meter recorded how much generation it saw for the month. So 600 kilowatt hours at 7.7 cents and 508 kilowatt hours at 9 cents. So that was a total of 1,100 kilowatt hours exported to the grid, which then, and here's the delivery and regulatory charges that are credited, and then the total credit. So then the utility does the math and says, here's your expense, here's your credit. So the bill ended up, and remember, as I said, there are charges that don't get offset by solar. So that is HST and the monthly account fee. And so that is the amount the homeowner pays. And then this is the amount of credit that is carrying forward on the bill into the next month. And so, essentially from our model, how does solar stack up? How does it compare to energy consumption? Well, as the sun moves through the sky, so this is June 21st, this is December 21st, so the sun is higher in the sky, higher on the horizon in the summer and lower on the horizon in the wintertime, and it follows this sort of path through the seasons as it moves east to west from sun up to sundown every day. Well, we end up with an irradiance, a monthly irradiance that differs greatly from winter to spring to summer to fall, and we end up with a tilt and orientation factor and a total solar resource factor for each home and each site, which then tells us how close we're going to get to how much energy is being consumed. And so we have the ability then to say, okay, based on generation and based on consumption from anticipated consumption from the energy model, here's what our bill is going to look like before solar, And so it lines up directly with that distribution of energy consumption. And here's what our bill is going to look like after solar. And it doesn't go to zero because, again, we always have that fixed monthly fee that doesn't go away. And we're always paying HST on energy consumed, no matter if we're offsetting it or not. So we have some amount of energy bill each month. It's never to zero. So what we see is that for this home, pre-solar, we could have expected to pay about $200 a month in electricity bill. And now post-solar, we're expecting to pay about $34, $35 a month. So it's a bill offset of about 83%. And now once we take that bill offset and we say, okay, generation, consumption, savings, we put that into our financial model. We model the project life at about 25 years. And we factor in our 0.3% per year in degradation of performance of the panels. We have a monthly O&M cost factored into our model. And this is in consideration of, at some point, we may have to replace the inverter. And if that happens after warranty, which is 12 years by default, extendable to 25, we have a built-in cost there that covers that. And we have a cash flow discount rate for net present value of money at 4.5%. So what that turns into, if the cost of this system is almost $29,000, and we are offsetting electricity that has a rising cost of about 7% per year, which is based on the historical average, then we see that the system pays for itself in just under 10 years. And so each year, we're sort of, as utility rates increase, we're paying down a greater percentage of that, of the total cost of the system. We see our break even just around 10. And then after that, the homeowner is cash flow positive, which means that the system benefits, which are the savings from the generation, are greater than what the cost of electricity or the cost of the system was. And so then this is additional cash flow for the homeowner. If it goes on the loan or the mortgage at time of construction, and we factor in about a 6% mortgage rate, which hopefully is high and we're not going to see for very much longer, then what we see is this almost $29,000 at 6% on a mortgage will add about $186 per month to the mortgage cost, which, you know, offset against $170 per month in savings in the first year. We're slightly cash flow negative. We could say almost cash flow neutral. And then each year as utility rates increase, we see the benefit to a greater and greater extent. And so by about year 6, 7 on, there's definite financial benefit through additional cash flow in the home, having had gone solar and putting it on the mortgage. In addition, there's definite environmental benefits. So the grid in Ontario has become pretty clean over the last 10 years. We've shut down all of our coal-fired plants. Our nuclear facilities are quite aged and do need some refurbishing, which is going to be a very capital-intensive process. But we do consider nuclear generation to be carbon-free, even though there is nuclear waste to deal with. And we have a great amount of hydroelectric and an increasing amount of renewables. And so even still, you know, the benefits of the amount of generation that the model home for Landark is going to produce over the course of the year is the equivalent of planting 5,200 trees, of not burning 475 barrels of oil, or in planting 168 acres of forest. Okay, so I'm going to pause there once again. This is the last section that we're going to talk about. Kevin, Stephen, any points at this point?
Oh, this is great. Well, I think if we go through this, we're getting some great questions coming in, and we'll catch those at the end. So,
okay,
yeah, thanks. It's great to see that it works. Yeah, the business case works well for, you know, either for a cash purchase or, you know, somebody who wants to put it into their mortgage, and you know, we know that, you know, you're investing in an asset too, so that this is an asset that has value beyond just, you know, just beyond cash flow. It also is increasing the value of the home because of this, you know, the energy savings that it offers, right? So that increases the value of your asset. And yeah, great to see that the systems that have been on houses for, for more than 2 decades are still generating significant power too.
Absolutely. Okay, so let's talk about monitoring system performance, because it is critical to ensure that your asset is performing as designed and continues to do so over time, and that we receive notifications and alerts if anything goes wrong, which time to time does happen, although it is rare. And so we install, with every system that we design and build, we install an energy monitoring system that monitors the performance of the system, provides those alerts, as well as monitors energy consumption within the home, and then tells us what's going to the home, what's going out to the grid, what's coming in from the grid, and gives us the net sort of readings over time. So here's a monitored system. This is what a solar generation curve looks like in a typical perfect cloudless sunny day. We see the system start to produce around 6:30, 6 o'clock this time of year. This is taken from June 17th. We see power production ramp up through the day. And then as we get to solar noon, which in this location is not actually noon, it's closer to sort of 1 p.m., we hit the peak, and then we sort of hold that peak throughout the afternoon. And then as the sun starts to set on the other side, we start to drop off generation. The green is consumption within the home. So this is, as you would expect, biggest loads happen sort of in that 7 to 9 a.m. range in the morning, and in that 5 to 7, 5 to 9 p.m. range in the evening. And so where we see the solar generation curve above the loads being consumed in the home, all of this is excess energy that's being exported to the grid. And so what that looks like is we have, our monitoring system will tell us, and this is high level, we can get a lot more granular, but for the purposes of this presentation, I think this is sufficient. We have a solar array producing energy. We have some of that energy going to the home. We have the remainder going out to the grid. Here's overnight. Here's energy generation starting in the morning. And then generation versus consumption throughout the day. This is all excess. And so we can see here that we produce 76.2 kilowatt hours this day. The home consumed 38.3 kilowatt hours. We sent 55.7 to the grid, and we purchased 17.8 from the grid. So we're purchasing energy overnight here, and in the evening here, and in the daytime, we're exporting all this excess here. So the net difference was we sent 37.9 kilowatt hours to the grid, and that's the credit that the homeowner is going to carry forward into the next day. And then over the month, that credit accumulates, and that's what carries forward into the next month. And this is sort of, a 7-day screenshot here of solar energy consumption, and you can see the overlay. Now, how this looks. So when we are in a situation where we're generating exactly the amount of energy the home is consuming, and we're not exporting to the grid, and we're not pulling from the grid, and this scenario happens most typically when we have energy storage involved. So excess power is going into a battery within the home as opposed to out to the grid. Here's the interaction with the grid: 0. On a day where we're generating more energy than is being consumed, you can see where we're exporting the excess energy here. And on a day where we're relying on the grid during the evening or nighttime hours, we're sort of doing so this way. And then the sun comes up, we're completely supplying the home, so 0 energy from the grid, excess goes out to the grid, and then 0 energy from the grid. And so systems can be programmed to either export all energy to the grid, charge a battery bank, or simply load follow, which means we're only generating what the home requires, and we're not generating any additional, and we're not sending any out to the grid. Okay, so some FAQs. We talked about net metering, I think, sufficiently enough here. If there's any questions, I'll address those. How does solar impact property value? Kevin mentioned this already. We definitely see an increase in property value due to energy generation from the system, which offsets utility expense, which means that you're more cash flow in the homeowner's pocket. What happens when it snows? This is a common question. So when we get snow on the array does not generate at full capacity. We have essentially a small amount of voltage and current in the system, which when the sun comes up, allows the system to the glass of the modules to heat up. And when solar modules are operating, they're typically at about 20 degrees hotter than ambient temperature. So any snow on the roof is going to be shed throughout the course of the first couple of days after a snowfall, and then the system's going to be fully operational again after that. But while the panels are covered, we're not going to have a significant generation. If there's no battery bank involved and the grid goes down, the solar array shuts down. And this is a protection mechanism so that we're not feeding back onto the grid when it's possible that there's going to be service workers out, doing service on the distribution system. So this is a code requirement. And unless there's batteries, the solar array shuts down, the inverter does not output. There are no annual maintenance costs. There's no moving parts in the solar array. The inverter is solid state. There's no moving parts or mechanical parts within the inverter. So everything is sort of digitally controlled or very low tech in terms of the PV module themselves, where we have sunlight knocking, photons and sunlight knocking electrons loose within the silicon wafer that then start to move through a circuit, which creates current. And so in terms of maintenance cost, annual maintenance costs really are actually zero. And manufacturer warranties line up almost completely with the 25-year life term that we put on the analysis. If I need to replace my roof, so on a new home, you're not going to need to replace your roof because the PV system is actually going to prolong the life of the shingle. It shields the asphalt shingle from direct UV exposure as well as any impact from the environment or the elements. And we've seen shingles underneath the PV system where the remainder of the roof exposed to the sunlight was in very bad shape, and underneath the PV modules, the shingles were actually almost like new. A system is going to last 25 years and well beyond. So manufacturer warranties are 25 years, but the actual life expectancy of a system is 30 years plus. And we've seen this. There are systems that were installed in the 60s that are still producing energy today almost as efficiently as they were 40, 50 years ago. And as technology becomes more efficient, panels will not be out of date. Simply what happens is we can achieve an equivalent amount of generation on less square footage. And so that doesn't translate into your technology is now out of date. It translates into, were you to do the project today, we would not require as much roof space. So there will actually not ever be a requirement to upgrade solar modules to newer efficient modules if the amount of electricity that's being produced from the array still meets your needs. If more is required, then that's the point at which it would be relevant to look at adding newer, more powerful, more efficient modules. But unless that's the case, there'd be no requirement. And then, will the fire department let my house burn down if there's a fire? Emphatically, unequivocally, the answer to that is no. We have actually installed systems on the fire department headquarters in Guelph, as well as numerous fire stations around Wellington County and other areas. So this is a myth. It is not true. They will come to your house and they will deal with the fire. Let's hope that never happens. Okay, so I'm going to actually just go right into questions here in the interest of time. So Kevin, Stephen, let her rip.
Well, first question is from Jim. Does this modeling assume no battery backup?
So the actual generation model for the solar array does not consider battery backup in the model because it is independent thereof. Any charge for a battery happens after power is generated by the array, so it doesn't affect the efficiency or the performance of the array in any way. So if we do or do not incorporate energy storage into the model, it doesn't actually affect the generation model for the system.
Yeah, that's great. Thanks, Will. And we have a couple of questions from one of our homeowners that are sort of linked into the the microfit program. So there was sort of a question of what about the excess stuff? Can I generate? Can I over generate? So you might want to just talk about the regulation around the way net metering works. And then the second part of the question was sort of around, again, sort of similar to the HST, to the microfit, just around the, kind of writing off the HST. So again, sort of related, I think, to the microfit model, but maybe you can just talk about how regulation has changed, and then yeah, just how the net metering system works now with credits and debits.
Okay, so yeah, the utility does not want to incentivize individuals from constructing and connecting generators that are going to net export. And so the way the regulation is written, if a generator is in a positive credit situation for 12 consecutive months, the credits on the bill are reset to zero, and then things move forward from there. The homeowner gets no credit for any credits that are carried forward for greater than 12 months and reset to zero. And so that is specifically written into the regulation to prevent homeowners from building generators that produce more electricity than they actually need for their home, because the program is designed and meant to allow homeowners to offset their electricity, but not put any more back onto the grid than what they are consuming, so that it's net zero over the course of the year. So there's no mechanism under the net metering program to get financially compensated for any excess generation beyond what is required for the home. And there's actual financial penalty if the solar array is built too large and creates too much excess energy. So that's a point to consider. And then in terms of tax incentives, you are officially, so a homeowner who is net metering officially becomes a generator under the distribution system code. So in terms of, how you decide to sort of operate that, from a personal standpoint or a business standpoint is completely up to the homeowner, but there is absolutely a possibility that as a generator, you can operate that as a business and claim HST back and take advantage of other tax incentives within the home that you would incur to operate your generator on an annual basis.
So Will, can I just, that's really helpful. And I think if that new capability of operating your array as a separate entity, the array you put on your house could be your business, could be a small business, I guess is what you're saying. And if am I right that this capability is coming into place as of July 1st? Is that, am I right on that?
No, it's in existence now. Oh. So essentially, any homeowner that has a renewable energy facility, distributed generation facility, which in this case, we're talking about solar. So you put a solar array on your roof, you actually become classified by the province as a generator of electricity connected to the distribution system. And so, your business operation is to generate and supply electricity to your home with the excess going out to the grid for credit. And so that can be established under a business entity.
Thank you. Yeah, got it.
Well, another question has come in. Does this design allow for 2 electric vehicles?
So this particular design does not. It doesn't. It only incorporates the calculations for the home, for the design of the home, with a limited amount of lifestyle or occupant loads that are based on the National Resources Canada prescribed amount. Those do not include at this time electric vehicles, but it's actually a very relevant point to the conversation, because if the homeowner knows that they already own or are going to own an electric vehicle at any point in the near future, then it is prudent to design a larger system to account for the additional energy that's going to be required to charge that vehicle. But that is not factored into the energy model. So it's not factored into the PV design. It can very easily be with a conversation ahead of time that says, hey, we have a Tesla Model 3 and a Model X, and we drive, 75 to 100 kilometers a day each. We can do the math. We can then increase the capacity of the solar generator in order to provide additional electricity to compensate for that load.
Great.
And we have a couple of questions, Will, around power outage, and I think this will lead into one of the email questions that we had. So let me just feed a couple of questions into this, and then you can talk into it. So there's a question. One of the questions is, what happens when the power's out for 2 days? Another question is, hey, could I also have a backup generator, a transfer switch, or a way of having a backup generator as well as solar? And that'll lead into the big question, which is, what's possible in terms of managing an extended power out with battery technology and that sort of thing. So maybe I'll let you do the first couple, and then I'll give you the very specific example that one of the interested clients has left us with.
Okay, yeah. So absolutely, can integrate backup generator with solar, no problem. Essentially what happens is the transfer switch gets installed. Instead of the inverter feeding back to the main electrical panel, the inverter feeds back onto the transfer switch. And that way, in the event of grid outage, we don't ever have a scenario where the generator is operating and providing power to the home, as well as the solar generating and providing power. And that power is sort of not being handled very well by the generator. And so the transfer switch ensures that the generator is neither exporting power to the grid during an outage or feeding back to the solar array, creating a loop that then feeds back to itself. So, because remember, I stated in the presentation earlier that when the grid goes down without an energy storage system, the solar array stops producing electricity. And so, the best way to do backup power, or not the best way, sorry, the lowest cost way of doing backup power still at this point in time is with a gas powered backup generator transfer switch. Absolutely possible.
And Will, I think I'm going to put you on the spot here. I think we've talked about, you could, perhaps come back and do another webinar in a matter of a few weeks anyway, that could get more into the backup, because we've got a lot of questions about, battery backup and what's feasible and what's economically feasible and that sort of thing. So let me just feed in the one question that gives you an example, but I want to just sort of let the audience know that we've talked about it. We're doing some interesting things in the model home, as you pointed out, where which we can, have you share your wisdom on in terms of, backup and smart energy management systems and that sort of thing in another webinar. But here's the specific question, and you can see where there's quite a lot of interest in terms of cost, effectiveness, and what's the right way to go about this. This question was, hey, if on December 21st, we've got a 3-day power outage, can I get enough panels on my roof and enough battery to run at 80% for, of my needs for 3 days? So I'll throw that over. It's a big question. But it is, we certainly are excited about the fact that we've got people that are, really thinking about the opportunity to, have a real resilient, we're building a better house. It's a resilient product as built, and now we're putting renewable on it. And how do we enhance resiliency for some of these extended outages that we're seeing?
Okay, so I guess the best way for me to answer this question is to sort of address the quality and construction side of the home first, because a net zero home, which we classify as a very high performing home, even or net zero ready, are very high performing homes, and they currently actually are 5 code iterations better than a standard code built home today. So we have a tiered structured sort of path for building code in Canada, and the net zero home sits 5 levels of improvement away from where we're at today with code. And so what that means is that the operation of the home is significantly improved. And so it experiences much less leakage due to air sort of exchanges. We call those air changes per hour. Insulation values are much higher. Triple pane windows are a standard requirement. And so when we talk about a net zero or net zero ready home, we have to understand that the energy requirements for that home, on a day-to-day basis are much, much lower. In addition, we've done some pilot projects and some studies as to how that home is going to perform with no power. And so, we look at June 21st and we look at December 21st for our heating and cooling loads, or actually it's probably more realistic to look sort of August, September for heating loads now, December 21st in and around that for cooling loads. And the reason why I think the individual that asked the question specified December 21st, winter solstice. It's when the sun is lowest on the sky. We have the shortest day of the year, the least amount of sunlight. How much energy is the solar array going to be able to produce for the home and the battery bank? And so the reason why I say, we have to take into consideration how much higher performing a net zero ready home is that it's going to require much less energy to operate in a grid outage, and it's going to hold. And so we looked at, a net zero home in a grid outage in the middle of winter. How long does it maintain temperature at a safe, habitable level for the occupant with no power? And that actually, it depends on temperature outside, but it actually looks like days, not hours. And so we don't require 80% of our electricity, typical daily electricity consumption to be available to us. We require much less than that. What that is specifically, I don't think we understand enough yet to actually say. But when we couple PV generation with energy storage, with energy management, which is what you alluded to slightly earlier, Kevin, then we can manage the loads in the home so that we set priorities, we shed non-priority loads, and then the priority loads are prioritized themselves so as in a situation where we're not producing solar and we have a decreasing capacity in the energy storage system, then as the state of charge drops, we start to shed additional loads, and that prolongs the amount of backup period that we have. And we do that without adding significant amounts of batteries and solar, significantly increasing capital expense for the project. So through energy management, with a typical net zero home, with the PV array for a typical net zero home, with a moderate amount of battery storage, it's absolutely feasible to keep a home operational for 3 days.
Brilliant. That's fantastic, Will. I know you've been very generous with your time. We're a little over an hour here. Are you okay if we just ask a couple more? We'd love to just ask a couple more of these questions. If Stephen, you good with that?
Yep.
Okay. Will, are you good for a couple more?
Yes. Yeah.
Okay. Awesome. We have a question about what happens if there's future shading from from a building beside somebody pops up a 2-story beside my house. Maybe there's a little bit of shading. Can that be taken into account, I guess, in the modeling, sort of understanding that? And then the second part of that question is any perspective on the impact of smoke, for example, that we've seen recently. Any perspective on that and what that might how that might fit into some of the modeling parameters you use for efficiency calculations?
Okay, so the first question was shading. Our software absolutely allows us to put whatever shading obstacle in the model we wish, whether it's a tree, a building, even if it's not there, we can model it in and we can determine what the impact's going to be. We've done a lot of residential work. We have modeled a lot of bungalows with 2 stories beside them. Typically speaking, the impact is minimal. If somebody were to put a 4, 5, 6-story apartment building right beside your home, that's going to have an impact. But somebody putting a 2-story in on the next lot, it's going to be minimal. We can definitely model that in, though, if anybody would like to see that. In terms of, wildfires and the resultant smoke thereof, which we actually just saw in Ontario here recently, we do model soiling into our generation forecast. And so, we have additional soiling factors throughout particularly the summer months, like June, July, August, September, particularly July, August, September, where we tend to get less rain, because rain is going to take care of that. A good rainstorm is going to completely wash the module surface off. It's going to remove any dirt, dust, and debris. And then, you're going to basically have a like new sort of equipment operating afterwards. during extended periods of weather where we don't have a lot of rain, particularly in a construction site where you're building a new community, and potentially with future adverse sort of environmental events like for wildfires. I think the soiling factor that we have already in the model is going to cover 95% of that. If we start to see things drastically change beyond what we're seeing now, we'd have to probably take a look at the model again. We might have some bigger concerns to be concerned about, though.
Well done, as usual, Will. Well done. So another question, what about storing the energy for efficiency and costs? Can a homeowner go completely off grid?
So a homeowner can go completely off grid. It would have to involve, so it would be a microgrid scenario. We wouldn't be looking at just solar with some battery storage. We'd be looking at more of a microgrid, which combines solar storage, a generator, and hardware and software controls to manage electricity, and to do so smartly, so that the system could support the homeowner's needs. There's a lot of sort of design that has to happen in the upfront side. It all has to happen behind a transfer switch. And in that scenario, what we'd be looking at is the primary power source for the home would be the microgrid, solar battery, generator as backup through the really dark months of the year, with a grid connection in the event that all of those systems are not sufficient and don't meet the aim. Then in that case, the grid comes in as the backup. It's a different lifestyle. It would require a sort of mentality shift and a different view of how you live and the amount of energy you consume and how and when you consume it. But I think it's definitely possible. Yes.
Well done, Will. Do you want to ask?
Yeah.
There's just two more.
We got two more. We got two more left. So almost done. One more question on the backup, and maybe we can pull again. I think we're looking forward to having you back, Will, when you're available. What is the typical cost of a backup battery system compared to a gas generator? I guess the question was about natural gas, but since we don't have natural gas, just some sort of a backup generator.
Yeah, propane generator, natural gas generator, costs are going to be exactly the same. The only thing is going to be, the only variable is the fuel expense. So you'd have to have a propane tank on the property for a propane generator. But for a whole home backup generator, you're probably somewhere in that $13,000 to $15,000 range, and that's generator, transfer switch, electrical work, gas connection, all of your sort of permits and inspections. You're probably in that $13,000 to $15,000 range. For an equivalent sized battery bank to provide the same amount of energy that you would get from that generator, you're probably in the $60,000 range. So you can see a significant cost difference. Now, so we would not actually, so if we say, typically single detached residential family dwelling is going to have a 200 amp electrical service, and if they're going to have a backup generator installed, it's probably going to be a 20, 22, 24 kilowatt generator. We're not going to do 20 kilowatts of battery storage for that home. We're going to do 5 or 10 kilowatts of battery storage, and we're going to manage the power more smartly. So then the comparison is not 20 kilowatts to 20 kilowatts. It's 20 kilowatts to 10 kilowatts. And 10 kilowatts of energy storage will, that's sort of output. We're probably talking a capacity of probably 40 kilowatt hours. We're looking $25,000 to $30,000. So still almost double the cost. But then we eliminate fuel expense, we eliminate annual maintenance, we eliminate mechanical sort of internal combustion engine, spinning a turbine, or spinning a rotor inside of a stator where we have lots of opportunity for failure, whereas we have essentially a solid state piece of equipment that uses electronic components to do what we need it to do, and sits inside versus outside. So over time, I think solar and battery is definitely going to be the way things are done. As battery pricing comes down, it's going to be easily more achievable. Right now, your generator is your lower cost option, but it can be done with battery.
Well done, Will. Last question. What government grants are currently available?
So there's a Greener Homes grant. It's a federal initiative. It allows for up to $5,000 back on a project. And that's essentially the way that works. It's $1,000 per kilowatt installed, up to 5 kilowatts. So for every kilowatt a homeowner has installed, they can access a $1,000 grant up to 5 kilowatts, $5,000. In addition to that, the federal government is also offering up to $40,000 on an interest-free loan. So the interest is 0%. It's a 10-year term, and it's up to $40,000. So let's say the project is $30,000. The Greener Homes grant provides $5,000 back in grant, so that's $25,000. And then the homeowner accesses a loan for the remainder of that at 0% interest with 10 years to pay it back. Those are pretty favorable terms. That's what's available right now. In terms of small business, there's an investment tax credit coming. We don't have the details. We're expecting to see those probably by December. But that is going to look something like 20 to 30% investment tax credit. And that is only going to be available for businesses. So small, medium-sized businesses.
We covered a lot of ground. I'm amazed.
We went a little bit over. I apologize.
Fascinating. Well, it's very, very helpful. I think you've done a great job of answering a lot of questions. So thank you. Really, truly appreciate you. And we're pretty confident that this video will get a lot of viewing in the future too. We have been recording, and we'll get this posted in the near future. So thank you. We're thrilled with the work that your team has been doing on the model home. We think it's going to be a great use case for people who are interested in both battery and intelligent energy management from their smartphone. All right, it's a very exciting project that we're doing in the model home. So come and see us. We've got lots to show you, and you can see that we're working with we think the best firm in Canada for this, and Will Beardmore and his team from Bluewater Energy. So we think that's going to be it's going to be a great long-term partnership, and Will, as you can see, can come up with a great solution for you and your home.
And the next video we'll do at the model home with video capturing all of the technology that you're putting in there. So yeah, very exciting.
Thank you so much, Will, for your time.
Thank you both. Cheers.
Cheers.
Thank you, everybody. Really appreciate you and your time. Thanks for the questions, and hope to see you soon.
Bye, everybody.